Hello, cosmic explorer. If you're lying here comfortably, it's because you know there's something special about falling asleep while contemplating the mysteries of the universe. Have you ever stopped to think why we don't float away from Earth right now? Why the moon doesn't escape into space? The answer lies in an invisible, silent force that literally holds the entire cosmos together. Today, we're going to unravel the secrets of gravity, that mysterious force that keeps your feet on the ground and the galaxies in their eternal dances. And here's a question for you to ponder while you relax. If gravity is the weakest force in the universe, how does it manage to dominate absolutely everything on a cosmic scale? Throughout this gentle journey, I will use simple examples from your daily life to explain concepts that even Einstein took years to understand. And at the end, I will save you a fascinating tidbit about something that defies everything we know about gravity. Something that is happening right now, millions of light years away. Take a deep breath, relax, and let your mind wander as we explore the force that unites the universe. Imagine for a moment that you are floating in space, completely alone, with nothing around you. No stars, no planets, no light. What would hold everything together? What would prevent every atom in the universe from simply scattering in all directions forever? The answer is a force so fundamental, so essential, that without it, literally nothing would exist as we know it. Gravity is the force that holds everything bound to the universe. Without it, there would be no planets forming from clouds of dust. There would be no stars igniting in nuclear furnaces. There would be no galaxies majestically spinning through the ages. Everything would be just isolated particles floating eternally in the black void, never coming together, never creating anything. Gravity is literally the invisible glue of the cosmos. But here's something fascinating and somewhat paradoxical. It's the weakest of the four fundamental forces of nature. Think about it. The strong nuclear force which holds atomic nuclei together is trillions upon trillions of times more powerful. The electromagnetic force, which makes magnets stick together and allows you to hold objects, is immensely stronger than gravity. And yet, it is gravity that most dominates on a cosmic scale, shaping galaxies, stars, and the very fate of the universe. Why? Because gravity has two unique qualities. It never cancels out, and it acts over infinite distances. While electric charges can be positive or negative, canceling each other out, gravity is always attractive, always pulling, always accumulating. And the more matter you gather, the stronger it becomes. Look at the night sky if you can imagine it, and see the moon shining softly. It's not standing there by chance. Gravity keeps the moon in orbit around the Earth, trapping it in a dance that lasts billions of years. Every moment, the moon is trying to move straight into deep space, as any moving object would like to do. But Earth's gravity constantly pulls it back, curving its path in an eternal circle. Without this gravitational pull, the moon would simply drift away forever, disappearing into the black void of space, and we would be left here, alone, without the tides it creates, without the silvery glow that illuminates our nights. It's a delicate and perfect balance, maintained by a force you can't see, hear, or touch. And our own Earth. It is just one of 8 planets caught in the same gravitational dance. The Sun, that gigantic sphere of burning plasma, keeps all the planets locked in a perfect dance through its immense gravity. Mercury, Venus, Earth, Mars, the gas giants. We all follow precise orbits around the Sun, not because we want to, but because we simply cannot escape its gravitational embrace. It's as if the Sun were a deep well in the fabric of space, and we're all eternally rolling around its edges, unable to rise out, but also not falling straight in. It's a perfect balance between speed and attraction that has been maintained for billions of years. But what determines how strong this invisible attraction is? The greater the mass of an object, the greater its gravity. It's a direct and simple relationship. The Sun is immense, containing 86% of all the mass in the solar system, so its gravity absolutely dominates everything around it. The Earth is much smaller, but still has enough gravity to keep you firmly stuck to its surface and the Moon in orbit. And there's another crucial factor. The shorter the distance between objects, the stronger this gravitational attraction. It's like a rubber band. The closer you are, the stronger the pull. If the Moon were twice as far away, the gravity holding it to Earth would be 4 times weaker. If it were 3 times farther away, it would be 9 times weaker. The force decreases with the square of the distance, an elegant mathematical relationship that governs the cosmos. And here's something that should make you pause and reflect. The Earth pulls you down with its gravity, but you also pull the Earth back with yours. It's true. Every action has an equal and opposite reaction. When you jump, you're not just pushing yourself upwards, you're literally pushing the entire Earth downwards. The problem is that your mass is so ridiculously small compared to the Earth's that this movement is completely imperceptible. Imagine trying to push a gigantic cruise ship with your finger. Technically, you're applying force to it, but it's so massive that it simply doesn't move perceptibly. It's exactly the same with you and the Earth. You pull on each other, but only you feel the effect because the difference in mass is absurd. And this invisible force has a fascinating effect on the shape of planets. Gravity makes planets spherical because it literally pulls everything toward the center. If you had a planet that was initially irregular, with gigantic mountains and deep valleys, gravity would constantly work to smooth out these irregularities, pulling the mountains down and filling in the valleys until everything approaches a perfect sphere. That's why planets and moons are round, not cubic or pyramidal. Gravity has no directional preferences. It pulls equally in all directions toward the center of mass, and the natural result of this uniform pull is a sphere, the shape that minimizes the average distance of all the mass to the center. Now imagine something strange. If the Earth stopped spinning completely, gravity would still exist normally. You wouldn't float away. But there would be a subtle difference. You would feel your weight slightly greater at the equator than at the poles. Why? Because the Earth's rotation currently creates a centrifugal force that slightly counterbalances gravity at the equator, where you are spinning faster. Without this rotation, the effect disappears. And here's something many people don't know. Earth's gravity isn't the same everywhere on the planet. It varies slightly with altitude, the density of the rocks below you, and even the composition of the soil. Massive mountains create slightly stronger gravitational fields. Deep ocean regions with less mass below have slightly weaker gravity. Scientists even use special satellites that measure these minute variations to map the Earth's internal structure, find mineral deposits, and better understand our planet. It's like taking a gravitational X-ray of the Earth, revealing secrets hidden beneath the surface. Remember those iconic images of astronauts on the Moon, jumping in slow motion, floating gracefully before gently landing. That's because the moon has only 17% of Earth's gravity. Imagine weighing 70 kilograms here and suddenly weighing only 12 kilograms on the moon. You would feel incredibly light, able to jump 6 times higher, to move as if you were in a dream. But if you were to travel to Jupiter, the gas giant of the solar system, you would experience the exact opposite. Jupiter, being the largest planet by far, has the strongest gravity in the solar system. If you could somehow stand on its gaseous surface, you would weigh more than twice your weight on Earth. Your movements would be slow, heavy, and exhausting. And there are little tricks of gravity that we experience without realizing it. Standing on top of a high mountain slightly decreases your gravity because you are farther from the center of the Earth. The difference is minuscule. Maybe you weigh a few grams less, but it's there. Contrary to what one might think, at the bottom of the sea you experience a slightly lower effective gravity. Not because gravity itself is weaker, but because the buoyancy of the water around you counterbalances some of your weight. But up to this point we've been talking about gravity as a force, something that pulls. And for centuries, that's exactly how we thought about it. Newton described gravity as a mysterious force that acts instantaneously through empty space. But he himself admitted that he didn't understand how it worked, only that it did. Then came Einstein, and he completely changed our understanding. Gravity isn't just a pulling force, it's something much deeper and stranger. It's the curvature of space-time caused by mass. Imagine the universe as a large, stretched rubber sheet. Now, place a heavy bowling ball in the middle of it. The sheet bends, creating a depression around the ball. Now, roll a marble near that depression. It won't continue in a straight line, but will follow the curve of the sheet, eventually circling or falling towards the bowling ball. It's not being pulled by some mysterious force. It's simply following the curved geometry of the sheet. That's exactly how gravity works. Massive objects bend the space around them, creating valleys and curves in the very fabric of reality. And everything moves within this deformation, following the curved contours of space-time like boats following currents in an ocean. There's no mystical pull, just geometry, just the most natural path through curved space. If space can be curved, then everything that travels through it will also be affected. Even light, the fastest thing in the universe, is affected by gravity, being deflected when it passes near very intense gravitational fields. It's as if light were following a curved road, not because something is pulling it, but because the road itself is bent. This bending of light by gravity has an elegant name: gravitational lensing. When light from a distant galaxy passes close to a massive galaxy or cluster of galaxies on its way to us, the gravity of this intermediate object bends the light, functioning exactly like a glass lens, bends the light passing through it. The result can be multiple images of the same distant galaxy, or bright arcs in the sky, or even complete rings called Einstein rings. And these gravitational lenses aren't just pretty curiosities. They help astronomers observe galaxies so distant, so faint, that they would otherwise be completely invisible. The gravity of massive objects in the way acts like a natural telescope, magnifying and illuminating things we could never otherwise see. It's the universe giving us a hand to observe its most distant parts. And here's something fascinating about the history of our understanding. The modern concept of gravity only really emerged with Einstein at the beginning of the 20th century. Before him, for over 200 years since Newton, we thought gravity was an instantaneous force, that if the sun magically disappeared, the Earth would feel the change immediately and fly off in a straight line. But Einstein showed that this is not the case, that gravity travels at the speed of light. If the sun disappeared, it would take us about 8 minutes to feel the effect, the same time it takes for its light to stop reaching us. Gravity is not instantaneous. It propagates through space-time like ripples on a lake. And since we're talking about how strange and fascinating gravity really is, let's delve even deeper into this mystery. Remember when I mentioned that gravity is the weakest of the 4 fundamental forces? Let me put that into perspective in a way that will make you truly understand how impressively weak it is. Gravity is billions of times weaker than electromagnetism. Billions. Think about it. A small refrigerator magnet can lift a paperclip, overcoming the gravity of an entire planet. All the mass of the Earth is pulling that paperclip down, and yet a tiny magnet easily wins. It's almost comical when you stop to think about it. But here's the trick. The reason why this ridiculously weak force dominates the universe. It always acts attractively and over long distances, never canceling itself out. Electromagnetism has positive and negative charges that cancel each other out. The nuclear force only works over microscopic distances. But gravity? It always pulls, always attracts, always accumulates and works across infinite distances. It's like water dripping on a rock. A single drop is weak, almost insignificant. But trillions of drops over millennia can carve entire canyons. Gravity works the same way, weak but relentless, accumulating its effects over billions of years until it shapes entire galaxies. And gravity is truly democratic. It acts on anything that has mass or energy, no matter how small. Even between microscopic subatomic particles, there is a gravitational attraction, although it is so absurdly weak that it is completely dominated by the other forces. But it's there, connecting every particle in the universe to every other, no matter how distant. Now, let's revisit that revolutionary idea of Einstein's once more, because it's fundamental to truly understanding gravity. Gravity isn't a force pulling objects in the traditional sense. There are no invisible strings, no mystical magnets. It's simply the curvature of space-time created by mass and energy. Imagine space as a 3-dimensional elastic fabric. It's actually 4-dimensional, including time, but let's simplify. Now, the greater the mass you place on this fabric, the greater the curvature it creates, the deeper the valley in space-time. That's why massive stars, dense planets, and especially black holes dramatically shape the space around them, creating deep gravitational wells. And here's something that should completely change how you think about our planet orbiting the Sun. Earth is in constant free fall around the Sun. We're not stuck in a static orbit. We're literally falling continuously toward the Sun. That's what orbit really means. An eternal fall that never ends because our lateral velocity constantly misses our target. It's like firing a bullet horizontally. It falls towards the ground because of gravity, but it also moves forward. If you fired fast enough, the curvature of the Earth would mean that the ground falls at the same rate as the bullet, and it would never touch the ground, circling the planet eternally. That's exactly what the Earth does around the Sun. The Moon is doing the same thing to us. It too is in free fall around the Earth, constantly falling towards us but eternally missing, because its lateral velocity is perfectly balanced. What prevents it from falling and colliding with us is simply its speed of movement perpendicular to the fall. It's a delicate and beautiful balance. And what about those astronauts you see floating gracefully inside the International Space Station? Here's a secret. They're not outside of gravity. Gravity at 400 kilometers altitude is only about 10% weaker than at the surface. They are falling, along with the station, constantly towards Earth. But the station is also moving sideways so fast that it keeps missing Earth forever. That's why we call it free fall, or microgravity, not absence of gravity. They appear to float because everything around them is falling at the same rate. It's like being in an elevator whose cables have been cut. You would float inside it while everything else plummets along with it. Before we continue this fascinating journey, tell me, where are you watching from right now? Are you comfortably in bed, perhaps gazing out the window and imagining the stars outside? Or are you on a cozy sofa, letting your mind wander through the cosmos? Let me know in the comments. I love knowing that these curiosities are helping you relax and discover the universe before bed. And if you're enjoying it, consider subscribing for more cosmic journeys like this one. Now, back to the mysteries of gravity. Earth's gravitational force decreases as you move away from it, following the inverse square law. But here's something interesting. It never truly reaches zero. Technically, Earth's gravity extends infinitely into space, becoming weaker and weaker, but never disappearing completely. You could be in the farthest reaches of the observable universe, and technically, you would still feel an infinitesimal gravitational pull from Earth. It's so small that it would be completely overwhelmed by the gravity of everything else around it, but mathematically it exists. Gravity doesn't have a maximum range beyond which it simply stops working. And here's a curious fact about our own planet. At the poles, you weigh slightly more than at the equator. Why? The Earth isn't a perfect sphere. It's slightly flattened at the poles and bulging at the equator due to its rotation. This means that at the poles you're a little closer to the Earth's center, and therefore experience slightly stronger gravity. The difference is small, maybe 0.5%, but it's there. Now imagine an impossible thought experiment. A tunnel running straight through the center of the Earth from one side to the other. If you could somehow fall through this tunnel, ignoring the absurd heat and pressure, something strange would happen. As you approached the center, gravity would actually gradually decrease. Why? Because as you descend, more and more of the Earth's mass is above you, pulling you backward, while less mass is below, pulling you forward. The two forces partially cancel each other out. And at the exact geometric center of the Earth, you would experience absolute zero gravity, being pulled equally in all directions at the same time. You would float there, in the heart of the planet, weightless. And gravity is a patient and persistent sculptor. It determines the shape of planets through a simple but relentless process. The greater the mass of an object, the stronger its own gravity, and the more it can mold that object into a sphere. That's why large planets are always round. Gravity simply doesn't allow for significant irregularities in such large masses. But small asteroids can have bizarre, irregular shapes, resembling cosmic potatoes or giant peanuts. Why? Because their gravity is too weak to mold them into spheres. They simply don't have enough mass to generate the gravitational pressure needed to smooth out their irregularities. It's an interesting limit, where cosmic objects transition from random shapes to spheres. And on even larger scales, it is gravity that literally binds entire galaxies together. Imagine hundreds of billions of stars, each following its own complex orbit around the galactic center, all held together by mutual gravitational attraction. Without gravity, a galaxy would shatter in cosmic seconds, its stars flying in all directions like fireworks. And think about this. Without gravity, there would be no atmosphere around planets. The gases would simply float away into space. And without an atmosphere, there would be no life as we know it. At least not complex life based on breathing and protection from radiation. Gravity not only keeps you glued to the ground, it keeps the very air you breathe enveloped around the planet. Gravity is also a creator. Stars are born when gravity slowly, over millions of years, crushes giant clouds of hydrogen gas. As the gas is compressed, it heats up. Eventually, the pressure and temperature at the center become so extreme that hydrogen atoms begin to fuse into helium, releasing tremendous energy. A star ignites. All of this orchestrated by gravity. Similarly, planets arise when gravity patiently binds microscopic dust and small rocks together over millions of years. First, dust grains sticking together through static electricity. Then, pebbles attracting each other gravitationally. Then rocks, then asteroids, then protoplanets, and finally, complete planets. It's a slow but inevitable process, guided by inexorable gravitational attraction. And now, prepare yourself for something truly strange that Einstein discovered. Gravity influences time itself. The stronger the gravity you experience, the slower time passes for you compared to someone in weaker gravity. It's hard to accept. It sounds like science fiction, but it's absolutely real and proven. And you don't need to go to a black hole to see this effect. Extremely precise atomic clocks on airplanes, flying just a few kilometers above the Earth's surface where gravity is slightly weaker, literally run time a little faster than identical clocks on the ground. The difference is minuscule, mere nanoseconds, but it's real and measurable. In fact, the GPS satellites your phone uses have to constantly correct for this effect. They are in orbit where gravity is weaker, so their clocks run faster. If we didn't adjust for this, the GPS would be inaccurate by meters after just a few minutes. Einstein's relativity isn't an abstract theory. It's working in your pocket right now. Now that we understand the basics, let's really delve into the heart of what gravity is, because the deepest truth about it is so strange it seems like magic. Gravity doesn't pull. There are no invisible strings, no ghostly hands reaching through space. Instead, it bends space-time, and objects simply follow these curves naturally, like water flowing through a valley. Imagine again that stretched rubber sheet, but this time think of it as representing not only space, but also time. When you place a heavy mass on that sheet, it deforms, creating a depression. The greater the mass, the greater and deeper the curvature of space-time around it. And everything that moves there simply follows the curved geometry, without feeling any pulling force. That's why the sun's gravity keeps the entire solar system in harmonic motion. The sun isn't pulling the planets directly like a person would pull a rope. Instead, its immense mass creates a deep valley in space-time, and the planets simply follow the curves of this valley, eternally rolling around the edges without ever falling in or escaping out. It's pure geometry, not force. And that completely changes how we think about movement in the universe. The planets aren't fighting against a force pulling them. They're simply following the most natural path through curved space. It's beautiful in its elegance. And returning to Earth, there's something fascinating about how gravity subtly varies in different places on our planet. Gravity at the Earth's surface changes slightly depending on exactly where you are. It's not a perfect, uniform constant, but a slightly variable field shaped by mass distribution, altitude, and even rotation. In regions near the equator, for example, gravity is slightly lower. There are two reasons for this. First, the Earth is slightly bulging at the equator due to its rotation, so you are a little further from the center. Second, the centrifugal force of the Earth's rotation partially counterbalances gravity there where the rotational speed is higher. In regions closer to the poles, both north and south, gravity is a bit stronger. The Earth is flattened at the poles, so you're closer to the center, and there's no significant centrifugal force there to counterbalance it. The total difference between the equator and the poles is small, about 0.5%, but it's measurable and real. Altitude matters too. Great mountains, like the majestic Himalayas that touch the sky, have slightly less gravity at their peaks. Why? Simply because you are farther from the Earth's center. For every kilometer you climb, gravity weakens a little. At the summit of Mount Everest, almost 9 kilometers above sea level, you weigh about 3% less than you would at sea level. Now, let's talk about a phenomenon you experience every day if you live near the ocean: the tides. The moon causes the tides because its gravity pulls more strongly on the side of the Earth that is closer to it. It's a gravitational gradient effect, where the difference in gravitational force between the near and far sides of the Earth literally stretches our planet slightly. The result? The ocean water on the side near the moon is pulled slightly more strongly, creating a bulge. And interestingly, there's another bulge on the opposite side of the Earth as well, because the moon's gravity is weaker there. As the Earth rotates beneath these bulges, we experience high and low tides. The sun also generates tides on Earth, but its relative strength is less than that of the moon in the tidal effect. Why? Although the sun is immensely more massive, it is also much farther away. And for tides, what matters is not the total gravitational force, but the difference in force between the near side and the far side. The moon, being so close, creates a stronger gradient. Here's a powerful demonstration of just how weak gravity really is on a small scale. A simple refrigerator magnet, that tiny object that fits in the palm of your hand, can easily overcome the gravitational force of the entire Earth on a small metal paperclip. The Earth, with its entire mass of 6 sextillion kilograms, is pulling that paperclip down, and the little magnet wins. It's almost embarrassing for gravity. Now, imagine something strange. If the Earth rotated faster, significantly faster, the effective gravity would be even weaker at the equator. The centrifugal force of the rotation would increase, counterbalancing more of the gravitational pull. We might even feel a slight reduction in weight, making us lighter, more agile. What if the Earth spun fast enough, really absurdly fast? Objects at the equator could start to partially float, or even be hurled into space. Centrifugal force would completely overcome gravity. Of course, long before that happens, the Earth itself would break apart from the tension, so it's not something we need to worry about. But it's an interesting thought experiment. And here's something you experience every time you go higher. Gravity decreases as you gain altitude. Airplanes flying at 10,000 meters experience about 0. 3% less gravity than on the ground. Tall skyscrapers have slightly less gravity on their upper floors. Mountaineers on top of high peaks weigh less. It's a small but real effect. Let's revisit the International Space Station once more, because it's so important to understand this correctly. The ISS isn't in a zero-gravity environment, as many imagine. Gravity at an altitude of 400 kilometers is still about 90% of the force we feel on the surface. That's substantial. So why do astronauts float? Because the station is in constant free fall. It falls toward Earth continuously, but it also moves sideways so fast that it keeps missing the planet forever. And the astronauts inside are falling at the exact same rate as the station. Astronauts float because they are in constant free fall along with everything around them, not because of a lack of gravity. If the ISS were to suddenly stop its orbital motion and remain stationary in space, the astronauts would immediately feel their weight again as they and the station plummeted towards Earth. Weightlessness is really just free fall. Now, let's go to the opposite extreme of the gravitational spectrum: black holes. These objects arise when gravity becomes so absurdly intense that it literally overcomes all other forces of nature. When a massive star collapses, gravity crushes everything into an infinitely dense point, creating a curvature in space-time so extreme that not even light can escape. It's gravity taken to its absolute limit, creating something so strange that it defies our intuition. Space-time is curved so dramatically that it creates a region from which nothing can return, the event horizon. Crossing this boundary means falling eternally towards the central singularity, with time becoming increasingly distorted until meanings lose their sense. And here's something that should make you pause. Even light, which has no mass, is deflected by gravity. How is that possible if gravity affects masses? Because gravity isn't actually pulling the light, it's curving the very space through which the light travels. The light continues to travel in a straight line, but the straight line in curved space is actually curved. This effect is called gravitational lensing, and it is one of the most spectacular predictions of Einstein's general relativity. When light from a distant galaxy passes close to a massive galaxy or cluster of galaxies on its way to us, it is bent around the massive object, creating multiple images or rings of light. And these gravitational lenses aren't just beautiful, they're incredibly useful. Gravity can amplify the light from distant galaxies, allowing us to see them through natural lenses created by giant galaxies in between. It's like the universe providing us with natural telescopes, helping us see objects so distant and faint that they would otherwise be completely invisible. And gravitational lensing has revealed something profound and disturbing about the universe. When astronomers study how entire galaxies are held together, calculating the gravity needed to keep all those stars orbiting, they discover something strange. The visible mass is not enough, not even close. Galaxies should be falling apart, but they aren't. There must be something else out there, something invisible but massive, providing the extra gravity needed. That's why we infer the existence of dark matter, a mysterious substance that doesn't interact with light but has mass and therefore gravity. And there's a lot of it, about 5 times more dark matter than normal matter in the universe. And returning to the big picture, gravity is literally the architect of the cosmos. It is responsible for forming stars through the collapse of gas clouds. It gathers dust and rocks into planets over millions of years. It organizes billions of stars into rotating galaxies. It groups galaxies into clusters and superclusters. The entire large-scale structure of the universe is sculpted by gravity. Without it, the universe would be just a scattered sea of particles, hydrogen and helium evenly spread throughout space, never coming together, never creating anything complex or interesting. There would be no stars to forge heavy elements, no planets to harbor life, no galaxies to punctuate the darkness. It would be a dead and featureless cosmos, cold and empty forever. Gravity transformed the uniform chaos of the early universe into the rich tapestry of structures we see today. It is the fundamental creative force, the patient sculptor working through the ages, organizing matter into ever more complex and beautiful patterns. And now, as we approach the end of this relaxing journey, let's consolidate and deepen our understanding of this extraordinary force, because it's worth repeating and truly absorbing. Gravity is the weakest of the four fundamental forces of nature, but curiously, it's the only one that acts effectively over long distances without dissipating or canceling itself out. Think of it as a cosmic paradox. The strong nuclear force that holds protons and neutrons together is immensely more powerful, but it only works at subatomic distances. Electromagnetism is much stronger than gravity, but opposite charges cancel each other out. Gravity, weak as it is, simply keeps accumulating, attracting, organizing endlessly without distance limit. And here's why it dominates the cosmos so completely. It cannot be reversed. There is no negative gravitational charge that cancels out the positive. Mass always attracts mass. Always. It's unidirectional, relentless, cumulative. The more matter you gather, the stronger the gravity becomes, and the more matter it can attract, creating a self-reinforcing cycle that builds planets, stars, and galaxies. Now, imagine for a moment if something like negative gravity or negative mass existed. Theoretically, it could cancel out positive gravity, creating regions of anti-gravity where objects would be repelled instead of attracted. It would be revolutionary, changing everything we know about physics. But nothing like that has ever been observed in nature. All the mass we have detected produces positive gravitational attraction. And here's something important about how gravity works. It doesn't need air or matter to act. Unlike sound, which needs a medium to propagate, gravity works perfectly in the complete vacuum of space. It's a property of space-time itself, not something that travels through it like a wave in a medium. Back in the 17th century, Newton formulated an elegant law that describes gravitational force. It decreases with the square of the distance. It's a simple but profound mathematical relationship. This means that if you double the distance between two objects, the gravitational force between them doesn't halve, but falls to a quarter of the original force. If you triple the distance, the force falls to 1/9. It's a rapid drop, but it never reaches zero. Double the distance again, and it drops to 1/16. Keep doubling, and the force gets weaker and weaker, but mathematically it never disappears completely. It's asymptotic, approaching zero infinitely but never reaching it. But remember, Einstein completely revolutionized our understanding at the beginning of the 20th century. He showed that gravity isn't really a force in the traditional sense of something pulling through empty space. Instead, It's a curvature of space-time caused by mass and energy. Objects simply follow the curved contours of this distorted space-time, and the more mass something possesses, the more deeply it warps the fabric of space-time around it. Think again about that rubber sheet. A marble creates a tiny depression. A tennis ball creates a larger depression. A bowling ball creates a significant valley. And a star or black hole, they create deep abysses in the fabric of reality. This is why massive stars, dense planets, and especially black holes create giant gravitational valleys in space-time. And everything that passes nearby inevitably rolls toward these valleys, or orbits eternally around their edges, trapped in the curved geometry. And speaking of dominant mass, consider this. The Sun alone dominates more than 99% of all the gravity in the solar system. Why? Because it contains more than 86% of all the mass. The planets, asteroids, comets, dust, everything else together makes up less than 14% of the total mass. The Sun is absolutely dominant. And without that immense solar gravity, without that deep gravitational valley that the Sun creates, the planets would simply fly in a straight line through interstellar space. There would be no solar system, just a solitary Sun, and 8 scattered planets following their own paths through the galaxy, never to meet again. Now, let's go to the extremes. Black holes create curvatures of space-time so intense, so deep, that not even light can escape once it crosses the event horizon. The gravitational valley is so steep that the way back simply doesn't exist geometrically. It's like trying to climb an infinitely steep hill. Impossible no matter how much effort you put in. But here's something many people don't understand. Despite this terrifying power, outside the event horizon, the gravity of a black hole is absolutely normal. It's the same as that of any other object of the same mass. A black hole is not a cosmic vacuum cleaner sucking everything around it. If you keep a safe distance, you will simply orbit it as you would orbit a star. In fact, here's a fascinating thought experiment. If the Sun were magically replaced by a black hole with exactly the same mass, Earth's orbit wouldn't change at all. We would continue orbiting normally, although we would obviously freeze and die quickly from lack of light and heat. But gravitationally, no change. The mass would be the same, so the curvature of space-time would be the same. Returning to our own planet, Earth's gravity isn't perfectly uniform across the entire surface. There are lighter spots where you weigh a little less, and heavier spots where you weigh a little more. Why? Because the density of the rocks beneath you varies. Areas with denser rocks have slightly stronger gravity. For example, volcanic oceanic islands, formed from dense basaltic rocks, have slightly higher gravity than ancient continental areas made of lighter rocks. The difference is small, fractions of a percent, but special satellites can measure these variations, creating detailed maps of Earth's gravitational field. And altitude continues to matter. Mount Everest, the highest point on Earth, has less gravity than at sea level. Not because the mountain has special properties, but simply because you are farther from the Earth's center. Every meter you climb, gravity weakens a little because you are increasing your distance from the planet's dense core. Now, let's visit other worlds. On the Moon, with its much smaller mass and correspondingly weaker gravity, you would weigh about 1/6 of your weight on Earth, approximately 5% of your terrestrial weight, If you weigh 70 kilograms here, you would weigh only about 12 kilograms there. You could jump 6 times higher, move in slow, graceful leaps like the Apollo astronauts did. But travel to Jupiter, the giant of the solar system, and the story is completely opposite. There, you would weigh almost 2.5 times more than on Earth. Those same 70 kilograms on Earth would become about 175 kilograms on Jupiter. Your muscles would struggle to move. Each step would be heavy and tiring. Jupiter is the most massive planet in the solar system, and its gravity brutally reflects this. And when we reach the absolute extremes of the universe, we find the strongest known natural gravity, supermassive black holes at the centers of galaxies. These monsters contain millions or even billions of times the mass of the Sun compressed into relatively small regions. Their gravity is so intense that it distorts not only space, but time itself in dramatic ways. Near a supermassive black hole, time literally passes more slowly compared to distant regions. An observer falling towards the event horizon would see the outer universe dramatically accelerating, aging rapidly while they appear to freeze in time. It's the gravitational distortion of time taken to its absolute extreme, where the concepts of space and time begin to lose clear meaning. And now, we've reached the end of this relaxing journey through the mysteries of gravity. Let's explore the extreme limits of this force that binds the universe together. Gravity is so incredibly sensitive that even a small change in the Earth's mass distribution, such as melting glaciers or tectonic plate movements, subtly alters the exact shape of its orbit around the Sun. It's a delicate system, responsive to minute changes accumulated over millennia. And Einstein predicted something extraordinary in 1916. Gravitational waves, literal ripples in the very fabric of space-time, but they were so faint that he doubted they could ever be detected. It took almost 100 years, but in 2015 we finally captured these cosmic ripples for the first time. These waves are created by cataclysmic events, black hole mergers, neutron-star collisions, massive supernovas. When we detect one, we are literally feeling space-time vibrate like a giant drum being struck. And here's something amazing. When a gravitational wave passes through Earth, it stretches and compresses our entire planet. Of course, the change is absurdly small, smaller than the size of a proton, but with extremely precise lasers we can measure it. It's like detecting a change the width of a human hair in the distance to the nearest stars. Neutron stars take density to the extreme. Their gravitational field is so intense that a teaspoon of their matter would weigh about 1 billion tons here on Earth. It's matter compressed beyond any intuitive understanding. And about black holes, their extreme gravity doesn't come from infinite mass, but from finite mass compressed into an extremely small volume. Compress enough mass into a small enough space, and space-time curves so much that it collapses in on itself, creating a black hole. The event horizon marks the point of no return, where not even light can escape. Within this limit, all the physical laws we know begin to fail. It is literally the limit of current science, a frontier beyond which we cannot see or measure. Supermassive black holes dominate entire galaxies. Our own Milky Way revolves around Sagittarius A, a black hole with 4 million times the mass of the Sun, and gravity determines the shape of galaxies, molding them into elegant spirals, smooth ellipses, or chaotic irregularities. But there's a profound mystery. Without something we call dark matter, galaxies would fall apart. They spin too fast to be held together by visible mass alone. This dark matter responds to gravity, but not to light, making it completely invisible. It forms a gigantic cosmic web connecting galaxies across unimaginable distances, and returning to the final picture. Without gravity, literally nothing would exist. There would be no stars being born from clouds of gas, no planets forming, no moons, no you. Just particles floating randomly through the eternal void. Gravity transformed chaos into cosmos, randomness into structure. It is the only force that acts on truly cosmic scales, shaping not only planets and stars, but the very destiny of the universe. And in the distant future, trillions of years from now, when all the stars have died and the cosmos is cold and dark, gravity will continue to work silently, binding together remnants of matter, organizing even in the darkness. And here's the fascinating tidbit I promised at the beginning. Some cosmologists believe that the universe may eventually stop expanding and begin to contract. If this happens, gravity will pull everything back together. Galaxies colliding, stars merging, until the entire cosmos is compressed again into a single infinitesimal point. A big crunch that would close the cosmic cycle. And perhaps, just perhaps, this collapse will trigger a new Big Bang, restarting everything again. Gravity as the force that creates, sustains, and eventually recycles the universe itself. It's a profound thought to contemplate as you relax, about to fall asleep. You lie here, held gently against your bed by Earth's gravity, which in turn orbits the sun, held captive by its gravity, which travels through the galaxy held together by the gravity of trillions of stars and invisible dark matter, in a universe shaped and defined by this force from the very first moment after the Big Bang. You are part of this cosmic gravitational web, connected to everything through this fundamental and mysterious force. It is simultaneously humbling and inspiring. If you enjoyed this relaxing journey through the mysteries of gravity, please like the video and subscribe to the channel for more cosmic explorations that will help you fall asleep, discovering the secrets of the universe. Your support helps create more content like this. Good night, Cosmic Explorer. May your dreams be as deep as the mysteries of gravity and as vast as the universe it unites. Sleep well, knowing that you are safe, gently held in Earth's gravitational embrace, traveling through the cosmos on an eternal journey.